Namaste Bacho and welcome. Today we're going to tackle a very important topic from our unit, electrostatic potential and capacitance. We're talking about the effect of a dielectric on capacitance. Now I know it can sound a bit tricky, but don't worry. My promise to you is that by the end of this, the whole concept will be so simple and clear, you'll not only score full marks in your exams, but you'll remember it for life.
Okay, so before we jump into the physics, let me ask you a question. Have you ever seen a carpenter or an electrician use one of those small stud finder tools? You know, the one they slide along a wall and it beeps when it finds a wooden beam behind it? How does it do that? Is it some kind of magic? Well, it's not magic, it's pure physics, and the secret behind it is exactly what we are going to learn today.
So, to understand that secret, let's forget all the complicated formulas and definitions for just a moment. We're going to start with a very simple analogy. If you can understand this one little story, I guarantee you the rest of the topic will become crystal clear. Here it is, the whole secret in one sentence. A dielectric inside a capacitor is just like putting a sponge inside a bucket. That's it. Just fix this picture in your mind. A bucket is the capacitor, and the sponge is our dielectric. If you remember this, you've already won half the battle.
Let's explore this. Imagine the bucket is our capacitor. The water inside it is the electric charge, Q. And the level of the water, that's our electric potential, or voltage, V. Now, what happens when we put the sponge, our dielectric, into the bucket? The sponge soaks up some water, right? And because of that, the water level suddenly drops. The potential, V, has decreased. Now, to bring the water level back up to where it was before, what do we have to do? We have to add more water. So the sponge has allowed us to store more charge, more water, at the same potential, the same level.
Okay, so that sponge analogy gives us a perfect mental picture of what's happening. But in the exam, we need to write the official physics language, the NCERT formulas. So let's connect our simple story to the real deal. In physics, this soaking power of our sponge is given a name. It's called the dielectric constant, and we use the symbol K for it. It's simply a number that tells you by what factor the capacitance will increase. So the formula is super simple. The new capacitance, C new, is just K multiplied by the original capacitance, C original. If K is 5, the capacitance becomes 5 times bigger. Simple.
So you all remember the formula for a parallel plate capacitor, right? C equals epsilon naught A upon D. Well, when you add a dielectric, you just put K in the front. The new formula becomes C equals K times epsilon naught A upon D. Here, A is the area of the plates, and D is the distance between them. That's it. K is just a multiplier.
But what is actually happening inside that material? Why does it behave like a sponge? To understand that, we need to zoom in and look at the atoms. Let's see the step-by-step process of how a dielectric really, truly works.
Okay, let's break it down. First, between the capacitor plates, we have an external electric field. Let's call it E naught. Now, when you place the dielectric inside this field, its atoms or molecules get stretched and aligned. This process is called polarization. This alignment creates a tiny electric field inside the dielectric, called EP, which points in the opposite direction. It's like a small counterattack. So what's the net result? The overall electric field inside gets weaker. The new field, E, is just E naught minus EP. And as we know, a weaker electric field means a lower potential difference, V. Now think about our main formula, C equals Q by V. If V, in the denominator, goes down, then C, the capacitance, must go up. And that, my friends, is the real physics behind the magic.
All right, enough with the theory. Let's make this concept rock solid with a very quick, exam-style numerical problem. It will make everything clear. Let's say we have a capacitor with just air inside, and its capacitance is 10 microfarads. Now, we slide a sheet of paper between the plates. Paper has a dielectric constant, K, of 3. So, what will be the new capacitance? It's as simple as it looks. The new capacitance is just K times the original. So, 3 multiplied by 10 microfarads gives us 30 microfarads. See? It's that easy.
Okay, now for a very important section. Let's talk about the common mistakes, the silent killers. These are the small misunderstandings that can make you lose marks in the exam, even if you know the formula. So listen carefully. The number one mistake students make is thinking that a dielectric increases the voltage. No, bilkul nahi. For an isolated capacitor, the dielectric actually reduces the voltage. Remember our sponge analogy? The water level went down. The second mistake is thinking the dielectric itself stores the charge. Again, wrong. The dielectric is an insulator. It doesn't store charge. It simply creates conditions that allow the capacitor plates to hold more charge.
So here's a simple trick to remember this correctly. Just think dielectric equals damper. You know, like a shock absorber in a car that dampens the bumps. A dielectric dampens the electrical field. It weakens the electrical push. And what is that electrical push? It's the voltage. So a dielectric is a damper. It weakens the push, which means it reduces the voltage.
We're almost at the end. Let's quickly summarize all the key points we've learned and also see how this topic connects to what we are going to study next.
So, to sum it all up, first, dielectrics are just insulators that polarize when you put them in an electric field. Second, their main job is to reduce the net electric field inside the capacitor. Third, because of this, the capacitance increases by a factor of P, so C new is K times C original. And finally, the big advantage is that this lets capacitors store a lot more charge and energy. Now, understanding this properly is absolutely crucial for our next topic, which is the combination of capacitors.
And to finish, I'll leave you with a question to think about. If a high value of K is so good, why don't we just find a material with a K value of, say, 1 million and make a super-duper capacitor? What's stopping us? What's the catch? Well, the answer is related to another property called dielectric strength. Think about it, and we'll discuss it more in our next session. All the best with your study.